Alright, so welcome to the second tutorial of topic 3, formula, stoichiometry, and the mole concept. So a quick review from the last tutorial. The last tutorial, as we recall, we had studied the relative atomic we studied the concept of relative atomic mass. So there's something I forgot to mention, which is uh, Alright, it's not exactly something I need to mention exclusively. It's right there in your periodic table. If you just look at it, for instance, when the sodium has this underneath it, you'll see this. You'll see this underneath it. This is our um, relative atomic mass, or as we write it, AR. Yeah. So relative atomic mass is denoted by AR, and well, the AR of sodium is 23, and so the AR of sodium is 23, and as we discussed it in the last tutorial, the definition of relative atomic mass is like the average mass of an atom of an element compared to the mass of an atom of carbon 12 isotope, right? So let me go through that again. So relative atomic mass is the average mass of an atom of an element compared to 1/12 of the mass of a carbon 12 isotope. Right, that's pretty straightforward. So let's move to our new concepts we're supposed to cover today. I hope you can see it. Right, so the next objective we have is defining relative molecular mass, MR, and calculate relative molecular mass. And relative formula mass is the sum of relative atomic masses. So this is pretty easy as well. It's like, for instance, just a moment. Yeah, like for instance, we have sodium carbonate. Just a moment, please. Yeah, so we have, what's up with this? Right, so we have, for instance, sodium carbonate, which is Na2CO3. So basically, if we'll be asked to calculate the relative molecular mass or relative formula mass of N2CO3. Now, before we get into that, let me explain what we understand by the terms relative formula mass and relative molecular mass. Relative molecular mass is simply just, we studied relative atomic masses, right? So just consider the addition. For instance, in a compound like Na2CO3, there are three elements: sodium, there's carbon, and there's oxygen, right? So there's 2 atoms of sodium, 1 atom of carbon, and 3 atoms of oxygen. So what relative molecular mass or formula mass really means, you just add up the individual masses of each element, and then you just add all of that up, and the result you'll be obtaining is your relative formula mass or molecular mass of that particular compound, right? So for instance, the relative molecular mass or formula mass of Na2CO3 sodium carbonate is not again. Right. Okay. On a second. Yeah. So, gotta be kidding me. Right. So basically we have 2 atoms of sodium here, and as we can recall, the relative atomic mass of sodium was 23. So the total mass of sodium in sodium carbonate will be 2 into 23. It's pretty easy. And then the total mass of carbon in Na2CO3 is going to be like the AR of carbon, the relative atomic mass of carbon is 12, and from this can easily be deduced from your periodic table. And then in case of oxygen, total mass of oxygen here is 3 into 16. Oh, sorry, 3 into 16. Right, so the total mass is, since there are 3 atoms of oxygen, we multiply the AR of oxygen, which is 16, by 3. And then since there's only 1 carbon atom, we multiply the AR of carbon, which is 12, by 1. And then since the number of sodium atoms here is 2, we multiply the AR of sodium, which is 23, by 2. So the addition of all gives us, I guess, 46 plus 40, 48 plus 12, 60, 60 plus 46, 106. So basically we get 106. So this is our total mass of this compound, right? This figure, this number is known as the relative molecular mass or the relative formula mass, depending on the case or the scenario you're facing. What I mean by that is there are 2 types of compounds, right? There's ionic compound, there are covalent compounds, right? In case of ionic compounds, which this clearly is, we say the addition of all ARs, or addition of all atomic masses, is known as the relative formula mass. And in case this was a covalent compound, for instance, hydrochloric acid, HCl, then the case would have been like the total mass would have been 1, since there's just 1 atom of hydrogen and the AR of hydrogen is 1, plus added to the AR of chlorine, and the AR of chlorine is like 17.5. Just a moment, 35.5. So 1 plus 35.5, since there's just 1 atom of chlorine, so our total mass is going to be like 36.5. So this is the AR of, sorry, the total mass of hydrochloric acid or hydrogen chloride. So basically, in this case, in case of a covalent compound, for instance HCl, the total mass will be known as the relative molecular mass, since in covalent compounds exclusively, we call each particle of the compound as a molecule, right? In case of ionic compounds, you don't really go ahead and call each atom or each particle of this compound a molecule, right? This is in no way a molecule, right? But here HCl is a molecule, right? Since it's a covalent compound, right? But Na2CO3 isn't a covalent compound, which means it can't, in this case, you can't call this a relative molecular mass, since ionic compounds never exist as a molecule, never exist as molecules, right? So the compounds which exist as molecules can only be described by the term relative molecular mass. So basically, relative molecular mass is 36.5. In case of HCl, or in case of any covalent compound, you call this a relative molecular mass. And in case of any ionic compound, for instance Na2CO3, you call the total sum, the total amount, the total addition, a relative formula mass. So albeit both are the same, basically both are the addition of the total, both are the total masses of each element of all the elements in the respective compounds, but the names are different since the properties are inherently different. So in case of Na2CO3, you call the addition, you call the results you have, you call it relative formula mass, and in case of an ionic compound, and in case of a covalent compound, you call the addition relative molecular mass. So yeah, I guess that's that. So I guess we just covered the point F of our syllabus, which is defining relative molecular mass and calculating relative molecular mass as the sum of relative atomic masses, which we just did. So we're done with all that. So we'll move on. So we'll move on to the next thing we have, which is calculating the percentage mass of an element in a compound when given appropriate information. Percentage mass calculation. All right. So we'll once more have the example of Na2CO3, right? So you'll be asked to calculate the relative, the percentage composition of a particular element in a compound. For example, you'll be asked to find or to calculate the percentage composition of sodium in sodium carbonate, right? Or you'll be asked to calculate the percentage composition of hydrogen in HCl, or you'll be asked to find the percentage composition of oxygen in Na2CO3, right? So how do you do that? It's pretty straightforward. What you do is you just all right. So what you do is you just divide the mass of that particular element by the total mass, and then divide it, and then multiply it by 100 to get a percentage to get your percentage composition, right? So for instance, you've been asked to calculate the percentage composition of sodium in Na2CO3. What you do in this case is you calculate the total mass of sodium, the total mass of sodium atoms here in this compound, which is 2 into 23, basically equals 46 grams. And what you do next is you simply divide this value, this number, by the total mass of the element we're speaking about, we're referring to, which is 106, and then multiply it by 100 to get your percentage composition. Oh, that's a cool feature. Yeah, so you basically do that to get your percentage composition. So basically, when you've been asked to calculate the percentage composition of sodium in sodium carbonate, in 1 mole of sodium carbonate, you basically have your answer basically is 43.3962% or 43.4%. So this is your answer, right? I hope that's clear. That's all about percentage composition. And now, all right, there's something else I would like to mention. In our previous point, in F, finding molecular mass, calculating molecular masses as a sum of relative atomic masses. We've been discussing this over and over again. So what I forgot to mention here is, for instance, what if the coefficient of sodium carbonate isn't 1, as has always been the case in our discussion? What if it's 2, or like 2.5, or like 2.56, or like 99? What do you do in that case? Well, what you do in that case is, for instance, there's a 2 before Na2CO3, meaning there are two separate Na2CO3 particles, right? There's one Na2CO3 and there's another Na2CO3. All right. So when you're asked to calculate the total, or the relative formula mass in this case, the relative formula mass of 2 Na2CO3, what you do basically is just multiply this figure by 2 and see what you get. It'll be like 212, or I'm just showing it a bit more descriptively. Basically would be 212. Yeah. So that's simply what you do. So the relative formula mass of 2 moles, we call this a mole. We call this coefficient a mole. I'll be coming to this concept later on. Just for now, know that this coefficient has a name and it's known as the mole. So 2 moles of sodium carbonate has a total mass of 212 grams. So basically, the relative formula mass of 2 moles of sodium carbonate is 212 gram. What do we do in case of HCl? For instance, there's 2 here, right? What do we do? Just like before, we just multiply the entire thing by 2, since when we say there are 2 molecules, when we say there's 2 HCl, we inherently mean that there are 2 molecules of HCl present. There's like 1 HCl molecule and there's another HCl molecule, right? So it's as simple as daylight. You just multiply the mass of one, the relative molecular mass of one molecule, and multiply it by, you just take the relative molecular mass of one molecule and then multiply it by 2, right? So we'll be having 2 into 36.5, which will be like 73, I guess. Yeah, it'll be 73 if I'm not mistaken. Yeah, not. So make sure to mention the unit, right? The unit is always gram. The unit of AR is gram, and hence the unit of relative molecular mass, relative formula masses, all are measured in grams. The standard unit is gram here in chemistry. All right. So the relative molecular mass in this case, since this is a covalent molecule, the relative molecular mass of 2 moles of hydrogen chloride is 73 gram. I'm repeating that again. The relative molecular mass of 2 moles of HCl is 73 gram. I hope that's clear. Alright, so again. Right. So next, when we are asked to calculate the percentage mass of an element, for instance, when you're asked to right, so that's that. So when we are asked to calculate the percentage mass of an element in a compound, when the mole is greater than 1, or when the coefficient is greater than 1, what you do basically is, now consider if in 1 mole of Na2CO3 there was 2 for instance, you're asked to find the percentage composition of the same, you're asked the same question, that is calculate the percentage composition of you're asked to calculate the percentage composition of sodium in 2 moles of sodium carbonate, right? What you do in this case is first calculate the total mass of sodium here. So how many atoms of sodium do we have here? In 1 mole of sodium carbonate, or when the coefficient of sodium carbonate is 1, we had 2 atoms of sodium here, right? So when we have when the coefficient is 2, or when the mole is 2, we'll obviously be having 4 atoms of sodium. That's pretty straightforward, right? So 4 atoms of sodium equals 4 into 23, which is 92 grams, right? So there's something else that needs to be altered. See, what we saw earlier, that the percentage composition is calculated by taking the mass of an individual element, dividing it by the total mass of the compound, and then multiplying it by 100, right? So the individual mass of element here is 92 grams. The total is 212 gram and not 106 grams. This was the case when the mole of sodium carbonate was 1. But now the coefficient, or the mole, is 2. So you can't use 106 anymore. You need to use a new total mass, which is 212. So here we go. And here it'll be 92. I don't know what that turns out to be. Right. Right, come on. Give me an answer again. Alright, so if we see here is the percentage composition stays the same. So in any compound, your percentage composition stays the same regardless of the number of moles you have next to it or before it, right? So this is what I tried to show by never mind. This is what I tried to show by doing all this calculation. So basically, you don't need to necessarily multiply anything by 2, since you're multiplying both your numerator and denominator by 2. So basically you don't the 2's get cancelled out either way. Your numerator will be cancelled out by the denominator and vice versa, so you don't need to worry about multiplying the entire thing by 2 if your compound itself is entirely multiplied by 2, right? So the result is going to be the same, right? So that being said, we move on to our next outcome: calculate empirical and molecular formulae from relevant data, right? So let me alright, you can't erase that. Right. So empirical formula. So before we move into that, we just need to have a good idea of what the term empirical formula means. Right. So for instance, alright, for instance, consider the formula. Consider the compound C3H6, right? Propane. So consider the formula, the compound C3H6, right? Empirical formula is basically the simplest ratio of elements of each of the elements in a compound. So the simplest ratio of the elements in this compound is like 1:2, right? There's 3 carbon for every 2 for every 2 hydrogen atoms. There's one. For 6 hydrogen atoms, there are 3 carbon atoms, right? So if you simplify it, it'll be like CH2, since the ratio is 1:2. So this is the empirical formula of C3H6. Now, this is the empirical formula. I'll just be writing it E and F, right? So there's another term you need to be familiar with. It's your molecular formula. It's nothing much. It's just this. The molecular formula is just the original formula, untampered formula of a compound, right? So C3H6 is our molecular formula, and the simplified version of the molecular formula gives us the empirical formula, right? So the simplified version of MF leads us to EF, right? I hope I'm just clarify one last time. This molecular formula, when broken down or when simplified, will give us the empirical formula. I hope that's pretty clear, right? So now, one important thing to observe here is, see here, if you want to go for reverse engineering, if you want to go from EF to MF, what do you need to do here? You just need to multiply this empirical formula by 3, right? You just need to multiply the empirical formula by 3 to obtain or to go back to your molecular formula, right? Alright, so what if the formula was what if the molecular formula was C4H8? Would the factor have been 3 back then? No, right? The factor would have been 4, right? You needed to multiply. You would have needed to multiply the empirical formula by 4 in order to get your molecular formula. The empirical formula would have remained the same, since the ratio remains the same, 1:2. But you would have had to multiply the empirical formula by a different factor, right? A different number, a different constant, right? Initially you had to multiply it by 3. Now you need to multiply it by 4. So basically this number before is a constant, right? Is a constant. Not a constant, actually. It's a variable. It's a variable which may vary between compounds, right? So y step is to write n in place of 3, 4, or whatever comes up. So whatever comes up, you just replace it in place of you just place it in place of n, right? So for instance, here it's C5H10. The ratio is same, so the empirical formula will remain the same, but your n will now turn to 5. N will equal 5 now. So what I'm trying to get at is when you multiply your empirical formula by a variable, you get your respective molecular formula. In other words, we can write it as an equation. Molecular formula equals n into empirical formula, right? All right, we will be requiring this formula later on, so just highlighting it. I'll just keep it there, and I'll move on to our main lesson of this outcome. So what you need to do is, for instance, you've been provided. So when you're provided with a direct molecular formula, it's very easy to deduce its empirical formula, right? It's very easy to deduce its empirical formula. But for instance, when you're not provided with a molecular formula, when you're provided with mere information, without a direct molecular formula, basically you're not provided with a direct molecular formula. You're only provided with information relevant to the molecular formula. So in that case, how do you calculate your empirical formula, right? So the questions are let me get an example. Just let me get an example question. All right. Right. So basically, we are told. That in an oxide of phosphorus, we have you're provided with in an oxide of phosphorus, you have 1.55 gram of phosphorus, P, and you have 2 grams of oxygen. Using this information, you're asked to calculate the empirical formula of the mentioned oxide of phosphorus, right? So using this information, you're not provided with an actual molecular formula of this compound, right? You're just provided with this data. There's 1.55 gram of phosphorus. There are 2 grams of oxygen. So using this data or information, you're required to calculate or deduce your empirical formula, right? So what we do here is, I'll just finish it up quickly and then move on to explanations in the next tutorial. So what you need to do here is you make up 2 columns, like, all right, I'll just right, so basically you make up 2 columns, one for each element, phosphorus and oxygen. You then this is the first step. The second step is write down the masses you've been provided with, 1.55 and 2, right? Now divide both by their respective atomic masses, relative atomic masses. So the relative atomic mass of phosphorus is just a second, I'll just have a glance of what the relative atomic mass of phosphorus is. There we go. So phosphorus has a relative atomic mass of 31. Can you see it? 31, right? So we'll use it here. So 31, we'll divide 1.55 by 31, and then we'll divide oxygen by its respective, by oxygen's respective relative atomic mass. So the relative atomic mass of oxygen is 16. So oh great, so we divide it by 16, right? So what we will be getting here is, in case of phosphorus, we'll be getting 0.05, and in case of oxygen will be like 1 by 8 is 0.125, if I'm not mistaken. Let me just recheck. Yeah, so 0.125. The next, this was your second step, right? So the third step is you identify the smallest result you've obtained, which is a smaller figure, 0.05 or 0.125. It's 0.05, right? Now what you need to do is divide both by the smaller value. So the smaller value is 0.05. You need to divide both by 0.05, right? You divide this by 0.05, and then you divide this by 0.05 as well. This is your third step. So you get a 1 here, that's for certain, and here you get a 5, I guess. No, you get a 2.5 here. You get a 2.5 here, right? Yeah, you get 2.5 here. This is your ratio. This is the simplest ratio. So in your empirical formula, the empirical formula of this compound, of this oxide of phosphorus will be P1. You just write the subscript here, 1, and then O 2.5. This is your empirical formula. Simple as that. So the empirical formula of this oxide of phosphorus is P1O2.5. We do not prefer putting decimals or fractional values as a subscript of any element. So what we do is we'll be multiplying the entire thing by 2 so as to remove the fraction here. So we'll be getting P2 and O5, right? So that's it. This is our simplest ratio. This is our simplest ratio of this oxide of phosphorus, and hence this is the empirical formula of this oxide of phosphorus, which is P2O5. I hope that's clear. We'll complete the rest in the next tutorial. Thank you for bearing.